My name is Samuel Schlafer, and this is my Physics 2212 Lab 3 on circuits. A little introduction to this lab. The purpose of this lab is to predict circuit behavior computationally with parallel resistors, measure current potential, and explore capacitor and resistor behavior. For all of this, the system will be just the circuit and the surroundings will be everything else, but for the computational model, there will be no surroundings. It will just focus on the system being the circuit alone. Some fundamental principles behind this lab. First off, there's the node rule, which states that the current flowing into a node must be equal to the current flowing out of the node, resulting in a conservation of charge. Next up, there's the loop rule, which states that the sum of all the electric potential differences around a loop is equal to 0, which is a direct result of energy conservation stated in the node rule. And then finally, there's Ohm's law, which is probably the most important fundamental principle regarding this lab, which states that a current through a conductor between 2 points is directly proportional to the voltage across the points, otherwise stated as voltage equals current times resistance. So first off, we were told to predict the currents of I1 and I2 that would be measured by the two ammeters shown in the diagram below on the left. So using V equals IR, we are able to first add up the resistance throughout the entire circuit, getting 147 ohms, and then isolate I in the equation, V equals IR, and then plug in and solve to get 441 amps. So next we were asked what happens when we reverse the connections of one of the ammeters. So nothing actually happens and everything just remains the same. The math does not change. Next we were told to replace one of the ammeters with a voltmeter. What happens? So now the ammeter will read 0 because the voltmeter has a very high resistance, and the voltmeter will continue to read -3 because there's not a voltage drop in the circuit. So now what is the voltage drop across each part of the circuit? So using the loop rule, we are able to find the change in voltage across each part of the circuit. The three changes in voltage are labeled delta V AB, delta V CD, and delta V EF, which are +3, -0.96, and -2.04 respectively. So when you attach a voltmeter, the circuit changes. Why doesn't the ammeter reading change? This is because the voltmeter has a very high resistance and little charge is able to flow through it, and therefore the charge won't be able to reach the ammeter. Now replace the voltmeter with an ammeter in parallel with the 100 ohm resistor. What happens to the current through the other ammeter? So because the ammeter has low resistance, the electrons are able to flow through it instead, which will lower the overall resistance of the circuit. So the total resistance of the circuit, which was previously 147 ohms, is now just 47 ohms instead. So what is the total resistance of each circuit element? So using using V equals IR, we isolate R and get R equals V over I, and then are able to solve for each part of the circuit. So R47 we get to be around 48 ohms, R100 we get to be around 102 ohms, R of the wire is just 0, and then R of the ammeter is also just 0. So resistor capacitor circuits, when they're charging and discharging, you see there's a 1-to-1 ratio between ohms and seconds for both of them. Next, a 9-volt battery, a 200 mF capacitor, and a 30 ohm light bulb are connected in series. What is the RC value? So the predicted RC value when you plug in values is 6, and using Excel we're able to plot and get an experimental RC value of around 6.88, which is very close to the expected value. Some potential errors with this, obviously. Error number 1 is human error in stopping the stopwatch during the lab and the capacitor from discharging at the same exact time. And then error 2, just with online simulations, it's often difficult to accurately represent real-world scenarios since everything is idealized, which just isn't true in the real world. Some discussion questions. What if we used a real ammeter? So real ammeters actually have some resistance and not just 0, which would limit the total current and change some of the values. And then what if we used an actual battery and no resistor? So without a battery, our simulation would depict the capacitor charging instantly. However, real batteries do have some internal resistance and need time to build up charge.